Good evening, students.
Good evening, sir.
Good evening, students. Are you hearing my voice?
Yes, sir.
So yesterday we have discussed about the basic point in the coordination chemistry. Okay. Today we will continue that. What are the important points of the coordination chemistry? We'll discuss today. First, we will discuss about yesterday we discussed about the coordination sphere. So coordination sphere means in the complex, the central metal atom along with the unionizable ligands, are called, that will put it in the square bracket. So it is called coordination sphere. When you take the example, so this will be the example. So look at, I have written copper ammonium sulfate. Okay, if you have taken when you take in copper sulfate, if you put it in ammonia, you can get the tetramen copper sulfate. Okay. Okay. So now, when you are put it in the water, you have this set one time and another one this. If you are testing, you can get the sulfate. You can get the positive test for the sulfate. You will not get the test for ammonia and copper. It shows that it will form a different compound. So this is not ionizable. This is ionizable. So whatever ion is non-ionizable, which will bond with your metal atom, it's called as coordination sphere. So the species present in the coordination spheres are non-ionizable. The species present in the ionization sphere. So this is called ionization sphere. Outside of the square bracket. Generally, the chemistry we will use when this will become the concentration. Okay, so this bracket we can use for the subscript 4, 3, 2, like that. If you want to mention, we will use this square bracket. When you are using normal parenthesis, when you are using this square bracket, it indicate once for the complex, or otherwise it will indicate the concentration. Okay, well, now coordination number. The total number of ligand, neutral or negative ions attached to the central atom in the coordination sphere called coordination number of the metal. So when you are taking this, here the metal atom which is attached in the coordination sphere, you have ligand and metal atom. So this will become ligand, this will become metal atom. The other side that is called ionization sphere. Okay, that is not ligand. Okay. So the total number of ligand attached to the central metal atom in the coordination sphere is called coordination number. Now you look at the copper which is attached with ammonia. How many number it was attached? How many number, ma? How many number it was attached? How many? How many number it was attached?
4, sir.
So the coordination number is 4. Coordination number is 4. Okay. Now it is a monodentate ligand. That's why you are saying 4. If it is bidentate ligand, the coordination number will vary. Okay. Same way I will write some of the example. Ni NH3 4 times, then Cl2. Okay. Now, if you are seeing this, the 4 number, what is the coordination number? So nickel is the central metal atom. This is the ionizable one, and then you have the neutral one, ammonia. So what is the coordination number?
4, sir.
So it is a coordination number is 4. Now, if you are seeing we are writing a complex, now what are the things in the complex that we have to write? Okay. You write one complex, copper, tetramine, so here this will become ligand, and this will become, what is that number? That number indicate what?
Coordination number.
Very good. Coordination number. Okay. And so the square bracket which indicate coordination sphere. So what is this? What is this?
Central metal ion.
Central metal atom. And you have one more thing. So this will become ionization sphere. Okay. So you can see the board clearly, right? Is it visible, ma? Is it
Yes, sir.
visible? Oh, okay. If it is not visible, mean let me know. Okay. Now, so this will become the these are the things which are in your coordination sphere. Sorry, coordination compound, central metal atom, ligand, coordination number, coordination sphere, and ionization sphere. Now we have to calculate what is the charge on the central metal atom, or otherwise we can say it is a oxidation number. Okay, so we have to calculate what is the oxidation state of your copper, because copper will present +1 or +2. So what is the exact oxidation number that we have to calculate? Okay, so you know that the ligand may be negatively charged or it may be neutral one. Okay, so now we have to calculate how many it was, what is the oxidation state of your complex. When it for that you remember the charge on the complex is a sum of charge of constituent parts. Okay, the sum of charge on the central metal atom ion and its surrounding ligand. So we have to take a note that the sum of charge on the constituent is equal to 0 if complex is neutral. So complex we are classifying under 3 types. One is positive complex, negative complex, and then neutral complex. So what is a positive complex means? When the coordination sphere gaining the positive charge and the remaining part becomes the negative one, means then it is called positive complex. Whatever we have written, no, that is itself positive complex. So when you are removing sulfate, it will give 2+. So the coordination which carry a positive charge, then it become a positive complex. Okay. If the negative complex means when the coordination sphere bear a negative charge, this become negative complex. For example, K4FeCN6, potassium ferrocyanide. When you are removing 4K plus, that complex will bear FeCN6 times. The coordination sphere will bear a negative charge. Okay. Is it okay, ma? Is it clear? When the coordination sphere having positive charge, it's a positive complex. When the coordination sphere having a negative charge, it's a negative complex. Suppose NiCO4, nickel tetracarbonyl. It's a complex, but it doesn't have any charge. Then it is called neutral. Okay. Is it clear?
Yes, sir.
So it's a cationic complex or other positive or cationic. Cationic complex, anionic complex, and neutral complex. Cationic complex means the coordination sphere will carry what charge? The coordination sphere will carry what charge, ma?
Positive.
Positive. Anionic means the coordination sphere will carry a negative. Neutral means it doesn't carry any charges. Is it okay? Bhagat
Yes,
Kumar,
sir.
is it okay?
Yes, sir.
Okay. Now, so how to know whether it is a positive complex or negative complex? It's very simple. When you are writing a simple salt like sodium chloride, NaCl, always we write the positive part in the first and then negative part in the second. So likewise, when you are writing a complex, when the coordination sphere comes first and then remaining coming the second means it's a positive complex. When sum of the atom you are returning and then you are writing a coordination sphere, it's a negative. Nothing you are writing means it's a neutral one. Okay. Okay.
Yes, sir.
Is it okay or not? Is it okay or not, Pa? Shall we move further?
Yes, sir.
Yes, sir.
Okay. Now we are going to calculate the oxidation state. We will take copper, same complex will take for the example, and then SO4. When you put it in the water, it becomes CuNH3 4 times 2 minus. Okay, because S2 plus SO4 2 minus 2 plus. So the copper you are going to find out, that's why it's a X plus you have 4 ligands. It's a NH3 is a neutral ligand. That's why neutral ligand doesn't contribute. That means it doesn't carry any charge. That's why you put 0. That's equal to minus plus 2. 4 into 0, 4, and the X equal to plus 2. So what is the oxidation state of copper? Copper plus 2, or otherwise we can say Cu2. Is it clear? Is it correct? Is it correct, ma? Now you calculate. I will write one more. CO NH3 twice Cl4, the whole thing power 2 minus. You tell me what is the oxidation state of cobalt? What is the oxidation state of cobalt?
Sir, is it 2?
Mm-hmm.
2.
Yeah, then how? It's correct. How?
Sir, NH3 is neutral.
NH3?
It's neutral.
Okay. Cobalt is X plus 2 into 0 plus
4 into minus 1.
4 into minus 1, then is equal to minus 2. So X minus 4 is equal to minus 2, X equal to plus 2. Very good. So one more example you can try. Same copper compound. CO En twice Cl plus ONO. Okay, ONO ஒரு ligand. The whole power is 0. Now you tell me it's a neutral ligand. Now tell me what is the oxidation state of
For one, know what we should do, sir.
tell me pa. If you're telling correctly, it become very easy. Are you able to find out?
No, sir.
Okay, good. So now cobalt is X, plus 2 into En. En means ethylene diamine. Ethylene diamines, what is the formula? CH2, CH2, NH2. Now we'll see about the ligand also. Okay, NH2. So two sides it has. So it can donate both the sides. Correct? So it can donate both sides. It's a bidentate ligand, but it's a neutral ligand. That's why 0 plus 1 chlorine, 1 into minus 1 plus ONO nitrito, then 1 into minus 1 is equal to 0. Then tell me X plus 0 minus 1 minus 1. So X equal to plus 2. Okay. Okay. Is it clear?
Yes, sir.
Yes, sir.
Sir, can you explain?
Now we'll see about the ligand. Then it become very easy. Okay. Because if you are seeing the ligand only you are confusing. We will write one by one. Neutral and ligands. Okay. Shall I write this?
Sir, after 2 times 0, what you wrote, sir?
After
2x plus 2 times 0. After that, what you wrote?
no. I'm not getting. Pardon?
Sir, in the oxidation state, after x plus 2 times 0, what you wrote? Ethyl diamide, what you wrote after that?
2 times 0. That means
Yes, sir, after that, what you wrote?
1 into minus 1, 1 into minus 1. Chlorine will give minus 1. Nitrito, NO minus, it give minus 1. So 1 ligand into that oxidation state is minus 1. 1 ligand into minus 1. Okay. So I will write legibly. So you are taking CO, En twice, ClONO. It's the ligand. Okay. So everything you put it in the coordination sphere. So it gives 2 into 0. Correct? Correct. This gives minus 1. This gives minus 1. So that's why I written X plus 0 minus 1 minus 1 equal to 0. Because coordination sphere, in the above sphere you have 0 value. That's why. Okay.
Yes, sir.
Now I'm is it okay?
Yes, sir.
Okay. So now we'll see about the ligands. Then it's become very easy for you. First we'll have the neutral one. So name of the ligand also you have to keep in mind. Okay. Charge and name of the ligand. First, ammonia. Ammonia means NH3. It has 2 1. Okay. So charge becomes zero charge. Name become amine. Because it has one lone pair. And then second, water. HOH. So same zero. This is aqua or aqua. Anything you can write. And then third, phosphine. Most used pH3. So same zero, phosphine. அடுத்த nitrogen oxide. NO. Zero, nitroside. Please remember NO. Okay. And then carbon monoxide. CO. Okay. The charge becomes zero. Carbonide. So naming. How the name will come, no? That I am writing carbonide. Next, pyridine. Generally, they will put PY. Okay, PY means pyridine. C5H5N. That's also zero. Name pyridine. And then triphenyl phosphine. C6H5 thrice phosphorus. Zero. So same name, triphenyl phosphine. Okay. So these name, this name is coming for your monodentate neutral ligand. And then bidentate neutral ligand, we are going to write again. Bidentate, tridentate, that and all. Clear? For a neutral ligand, you have any doubts? This you should know. Then only it's very easy. Otherwise, it becomes difficult. Shall we proceed further?
Yes, sir.
Oh, sir.
Yes.
Sir, the density of carbon monoxide is 2. Then
Density of?
no, density of carbon monoxide is 2. Then if it's neutral.
Could you see that carbon triply bonded with oxygen? Okay, so that the oxygen will have that, no, it can.
Sir, so how does it become neutral then?
How?
Oxygen will have positive charge, no, sir. So how can it become neutral?
See, that carbon which is having that oxygen can donate the 2 electron to the carbon, so it become richer one. Okay, it can donate. So when you have the metal atom, it going to be participate in the coordination. Likewise, like this. So I have written, no?
Understood, sir.
Okay, because it's after it's not completed. So the 2 electron can be donated from oxygen to carbon. Now the carbon will become electron rich. This electron rich one will bind with your metal atom. Okay. Is it
Sir,
okay?
Sir, but if carbon forms a double bond with oxygen in this case, and then it will have 2 lone pair of electrons. So it can donate both the lone pair of electron for the coordination bond, right?
For the oxygen,
No, sir. If carbon is attached to oxygen, if it is attached with a double bond, so carbon will have. Okay. No, I got it.
Okay.
No,
I will tell you what you are asking. I could understand. When it become like this, no ma. Okay. When it become like ketone means now this oxygen can donate when it become RR group. Okay. Suppose
sir.
if it is in the carbon monoxide form, it will donate the carbon. In case of ketone, the oxygen will be a donor form. Okay. Suprajit, okay.
Sir, no, sir. I'm asking if the RR is not attached, carbon will have two lone pair of electrons, right?
If RR is not attachment, carbon octet is not completed, Nama.
Okay, sir.
So,
Understood, sir. Yes.
understood? Good.
Yes, sir.
So this is about the neutral monodentate ligand. So everything it's a monodentate ligand. Very good question you was asked, because when you are saying carbon, oxygen more electronegative, the oxygen only donate the electron. We may think, but in the carbon monoxide case, carbon will donate the electron. Okay, shall we go for the negative one? When you are writing the ligands, negatively charged means you have to add a name end with O. Okay. So negative ligand. So name end with O. That sound is it has to give sound O. Okay. So I can write CH3 COO minus. So this is known as acetate. Okay. Acetate. When it comes to that ligand, acetato. Could you understand? When you are writing, it becomes acetato. If it is X minus, halo. For example, Cl minus chloro, we will call. That name also chloro. This is IUPAC, International Union of Pure and Applied Chemistry form. Look here, now the last year or last before year, it has been changed to chlorido. Okay, in your book is not updated, you can write the chloro, but for your information, I tell you, the chloro has been changed into chlorido. The committee has been changed from chloro into chlorido. Okay, then if we are putting Br minus means bromo. Charge, this become -1 charge, this become -1 charge. The next Cn minus, cyano, Cn minus, so it charge become -1. Cyanide ion, the name should be cyano. And then oxide ion, common name first, whatever we are writing for O2 minus, the charge become 2 minus, then it said oxo. Peroxide ion, O2 2 minus, the charge become 2 minus, so -2 2 minus, whatever you can write, that name become peroxo. And then carbonate ion, CO3 2 minus, so charge become -2, carbonate. and sulfide. Sulfate. SO4 2 minus sulfate 2. Sulfate 2. Sulfite, PHIT, sulfite ion. That means SO3 2 minus. That is also 2 minus. That name is sulfito. Then sulfide ion. Yes, 2 minus 2 sulfido. So naming, look here, cyanide ion becomes cyano, oxide ion become oxo, peroxide ion become paraxo, carbonate ion become carbonato, sulfate ion becomes sulfato, sulfate ion becomes sulfato, sulfide ion becomes sulfido. So you have to see the charge. Oxygen means it can donate -2, peroxide means -2, carbonate means -2, sulfate means -2, sulfite means -2, sulfide means -2. So this you can keep it in mind. This become -1. Acetate means -1. Halo means -1. Okay. We have still more. That will put the next one. Shall I write? Shall I write this? Shall I rub ma? Shall I go further? So when you are
Yes, sir.
calculating oxidation state, it become -2. Okay. Still you have more negative ligands. That's why I'm worried. We will take the nitrogen oxide. Nitrite. That means NO2 minus 1. Before we have written nitroxide. Okay, now we are written nitrite -1. Charge become -1. Nitro or nitrito. Nitro or nitrito. So here you keep in mind it has linkage isomerism. So when we are studying about the isomerism, now it has a chance it can coordinate through nitrogen or it can coordinate through oxygen because nitrate ion become NO2O minus. Okay. So nitrogen lone pair also we have. So it can coordinate through nitrogen or it can coordinate through oxygen. When it coordination through nitrogen, it become nitro. When it coordination through oxygen, it become nitrito. Okay. Okay. Because it has this type of new ligands is called amphiphilic so this type of ligand is called amphiphilic nuclear what we can say ligands amphipoles. It has two sides, no, that's why it's a amphipoles. It can coordinate through oxygen or coordinate through nitrogen based on the metal atom. So what type of metal atom is there? If I have more affinity with oxygen, it can coordinate through oxygen. If it is more affinity with the nitrogen, it can coordinate through nitrogen. So based on that, we can say we can find out also which type of atom involved in the coordination. Okay,
Sir.
that's start. Yes.
Sir, but at a time only one it can only
Yes,
donate.
yes, it's a monodentate only. There is no doubt about it. It's a monodentate. It can coordinate it either through nitrogen or through oxygen. There is no doubt about it. Okay.
Sir, so it's amphidentate, right?
Yes, ambidentate. And the next, same. Suppose nitrate ion, NO3 minus. Okay, it's become -1 nitrate 2. Please remember, when become NO2 minus nitrate, NO3 become nitrate. So nitrito, nitrate 2. Okay, it's through oxygen. That's all. Because nitrogen become, it will be like this. Okay, now the lone pair is not available. Why it's not available? Because it involved in the already involved with one more oxygen. Correct? Is it clear, ma? So when you are taking nitrogen, the lone pair availability is not there because it already coordinated through one more oxygen. So it has only one oxygen which coordinate. If this oxygen or this oxygen, that's this oxygen. It will undergo what? Resonance. Next, it may be the coordinated one or it may be the coordinated one. That's why we can say it's a NO3 minus. Okay, we coordinate only through oxygen. And then sulfate, cyanide, we missed it. Thiocyanate. Thiocyanate ion. This is also one of the amp identity nucleophile, SCN minus. So this is also -1 thiocyanate. Why is it thiocyanate? Okay, because it is also involved in the isomerism, linkage isomerism. That's right. So we almost completed. We have still some of the things that we can. Hydroxide ion, OH -1. So -1, the name become hydroxo. When the oxygen involved means maximum hydroxide. NH2, amide ions. It become -1, imido. Oxo, paraxo, we completed. And then N3, acide. It become N3, N3 minus. It's very rare ligand. It become -3 nitrido. Why we are putting this charge? No, it will contribute to your metal oxidation side. That's why we are putting like this. Okay. Okay, ma. And oxalate. C2O4 2 minus. So then it becomes oxalate minus, because COO minus, COO minus. That means C double bond O minus, C double bond O minus. 2 minus is, that way charge become -2. Okay, okay, students. Okay, shall we move further? This is about your ligand state. Now we have to find out what is the oxidation state of the central metal atom. We will work it out 4 more things and then we'll move further. That means the coordination theory, Wednesday theory. Is it okay? Is it clear? Hydroxo, imido, nitrido, because next we are going to do only the IUPAC name. That's why. To take this example, you have to complete nickel tetracarbonyl. Okay, what is the oxidation state of nickel? 1. And then you take lithium Aluminium hydrate. What is the oxidation state of aluminium? You take sodium mercury cyanide. What is the oxidation state of mercury? And also you tell me what is that this is called ferrocyanide. Okay, Prussian blue. Otherwise it is called. You tell me first one. What is the oxidation state of nickel? Ax plus 4 into carbon. How much it will contribute?
0.
Hmm?
0, sir.
0. Very good. 4 into 0, 0. Then what is the oxidation state?
0.
Correct. It's a correct. So you go to the next one. Sodium means Na plus. Then coordination pair will have minus charge, right?
Yes, sir.
Am I right? You tell me what is the oxidation state of the mercury? Cyanide, what is that? That means Ax
So +1.
2 into minus 1. That's equal to minus 1. So X equal to plus 1. So mercury become plus 1. Correct. You come to here, lithium aluminum hydrate. Li plus Al4H4 minus. So here hydrogen is there, H minus. It will give minus 1. So X into 4 into minus 1. That's equal to minus 1. Then what is that?
Three.
Hmm?
3.
So plus 3 oxidation. So you coming here. If you work it out this one, you understood very clearly.
Sir,
X
is
is
it
equal to
2?
plus 2, sir.
Huh? What?
2
Plus 2.
Plus 2. How it is plus 2? Correct. How it is plus 2?
We will take minus 4, sir. As well.
Okay, very good. So you what you have to do, this 4 coming to here, this 3 coming to here. That means this is a positive part, this is the negative part. So Fe 3 plus and then Fe CN6 4 minus. And if you are finding, you will get that. Correct? Am I right?
Yes, sir.
This is called ferrocyanide. Okay, this is Prussian blue. What you will find out is very good, very good. So one more, only one thing that you discuss. Rhodium, rhodium, triphenyl phosphate, tell me. This is triphenyl phosphate. Okay, that will become trice.
Is it -1?
It is become
-1.
how it is minus 1 man. How it is -1? The coordination sphere will get the +1, correct? So coordination sphere will get the +1. X plus 0 is equal to +1. Then x equal to +1. That's all, no? And how you are saying it's a -1?
Yes, sir. +1.
Got it?
Yes, sir.
Because it's a neutral ligand. So neutral ligand, it contributes 0 charge, correct? So then it becomes 0. Is it clear?
Yes.
Just a minute. I will come. So when you are working out this type of problem, we will get an idea, because in the competitive exam, they will ask with the ligands of polydentate or neutral ligands only they will take. Okay, they will not take the easiest one, and they may ask. Okay, we will proceed further. Now, we can calculate ionization sphere. Is there? No. If the ionization sphere, it is chloride, right? When you have the chloride, we can calculate, we can find out. So we can calculate how many chloride atom is there, that also we can calculate. Okay. So how many ions present in the solution, that we can calculate. So when you are writing the amine complex of platinum, hexamine, Cl4. In the coordination sphere, what is there? Platinum, hexamine. Then what charge we will get in the above? What charge you will get, ma?
+4.
+4. And then you will get 4 Cl minus, correct? That means
Yes.
total number of ions in the aqueous solution. This is one type of ion, and you have 4 ions. Total, how many ions you have in the solution? 5 ions in the solution. Correct? 1 cation and 4 anions. Am I right or not?
Yes, sir.
Am I right or not, ma?
Yes, sir.
Now you tell me, I will write the formula. You have to tell me how many ions present in the solution. Platinum, NH3, twice, Cl4. For this, and then K.
Sir, 0.
What, ma? NH3 and Cl5. You tell me for these two, how many ions present in
Sir,
the
for the first one it's 0, for the second one it's 2.
For the first one?
0 ions are there, for the second one it's 2.
0 ion. For the second one?
2, sir.
Very good, very good. So we can find out this and this type of things also. Okay. And then next, we will go for the Bernoulli's theory. Okay. So Werner is the father of coordination compound. So he explained the nature of bonding in the complex. So only one thing he said, the metal has two different valency. One is primary valency and the secondary valency. With that, he explained all those things. Werner's theory of coordination compounds. So first he has taken the cobalt chloride. Okay. When the cobalt chloride mixed with ammonia, it will give different colors of compound with the different proportion of the ammonia. If they mix with the 6 moles of ammonia, it will give the orange color. If you mix with the 5 moles of ammonia, it gives the rose color. Then the same 5 moles of ammonia, it will give purple color also. For the 3 moles, it gives green color, violet color, and blue-green color. Then he wondered why it gives the different colors. Then he analyzed and successfully explained the properties of coordination compound in terms of structures was proposed by the Albert Werner. So in long before they don't have sophisticated techniques. Okay, even though they can give that brief outline of the coordination compounds. First, when you have the metals, it will consist of two valencies. When the metal will have primary valency and then secondary valency. Will consist of primary and secondary valency. When the primary valency, so generally we know that what is we will say valency. What we will say about the valency, ma'am? Generally, what we will call it as valency? Valence means what? What we will say as valency? Valence means what? Today up to 6:30 you have the chemistry class. Huh? Sir told me that up to 6:30 chemistry class. Tell me what is valency? Quick. We have to complete valence bond theory also. What is valency? Nobody having an idea about the valency? Shivani, what is valency, ma? Niranjan, what is valency? Say, am I audible?
Sir, the combining power of the elements, sir.
Combining
It's
part of
valency.
the elements. Okay. Then Shivani, what is valency? Shivani, are you there? Sriram, what is valency?
Sir, number of valence electrons in
Number of.
outermost shell.
Okay. Kanish, what is valency?
Sir,
Okay. So generally what we will say, the electron which are present in the valence shell, that means outermost shell of the particular element, we call it as valence electron. The ability to form bond, that also we call it as valency. So when you are taking an atom, it may have one valency or two valency. For example, when you are taking phosphorus, it has third valency and then five valency also is there. Because PCl3, PCl5 exists, no? Likewise, many molecules, tin chloride, SnCl2, SnCl4. So two different valency also have, it can have. So here what we are saying, metal have two types of linkage. Okay, well, that we are call it as valency. Okay, one is primary and another one is secondary linkage. So the primary valency or linkage, the primary valency will be satisfied by the negative ions. அதாவது it can be primary valency or satisfied by negative ions or positive ions. Okay, but it will be ionizable. So primary valency may be positive or negative. Okay, so it will be ionizable bond. Ionizable. And the secondary valency are neutral, it will be satisfied by neutral or negatively charged. So they are non-ionizable, which will present in coordination sphere. Okay, so the metal which has two types of linkage, one is primary valency or primary linkage, another one is secondary valency or secondary linkage. The primary valency always satisfy negative or positive ions. Okay, so it will be ionizable. So when you are testing, you will get the answer for that. The secondary valency, which are generally neutral or negatively molecule. Okay, they are non-ionizable, that will be present in the coordination sphere. Okay, now you tell me what is secondary valency? What is secondary valency? It's non-ionizable, which will be present in the coordination sphere. Metal and which one have in the coordination sphere?
Ligand, sir.
Very good. So they are ligand. So when you are saying the primary valency usually indicate, this will indicate oxidation state of the metal. Oxidation state of the metal. Because then the coordination sphere, it will reflect. The charge will be reflected in the coordination sphere. Ultimately, it will give the oxidation number of your metal. Whereas the secondary valency, which refers to what is that? Coordination number. Coordination number, which indicate what? It's become the ligands. That's all about the valency. Okay, and then the primary valency, they are non-directional and ionizable. It is equal to oxidation state of your central metal atom. So it is satisfied by negative ions. When they taken complex is positive. Okay. Secondary valency, they have directional. What is the meaning of directional? When you have the metal atom, so how that it will be oriented in the space. That's why we are saying secondary valency always directional. Okay, they are non-directional. The points in the points so totally 2 points. Metal has two valency, primary, secondary valency. The primary valency are non-directional and ionizable. It equal to oxidation state of the central metal atom. It is satisfied by negative ions. Because metal atom in our bone, metal atom will have what type of oxidation state? What type of oxidation state, ma?
Positive, sir.
Positive. That's why they are saying it will be satisfied by negative ions. It based on what type of ligand attached and what is the coordination pair having the charge. Okay, but it will be satisfied with the negative because metal will bearing a positive charge. That's why they have mentioned negative. That's why I also rub it as positive. Okay, and the secondary valency, they are directional, they are non-ionizable. It is equal to the coordination number of the metal. It's commonly satisfied by neutral and negatively charged ion, which is called ligand. So that also present in the coordination sphere. This will be present in the outside of the coordination sphere or in the ionic sphere. So it will present in the ionic sphere. It will present in the coordination sphere. That's all about the Bernoulli's theory. Nothing more. Is it clear? Is it clear, ma'am? Now, so based on the Bernoulli's theory, we have tried the formula for the cobalt chloride hexamine. Okay. Is it clear? You tell me what is that metal have? What type of valencies? How many types of valency?
2, sir.
Two.
Primary, secondary.
Primary and secondary. Primary valence means what are the primary valency? They are
Ionizable.
ionizable and directional.
Yes, sir. Non-directional.
Ionizable, it's satisfied by the negative ions. It indicates the oxidation state of the central metal atom and it will present in the ionic sphere. 5 points will be complete. In the secondary valency, they are directional and non-ionizable. They present in the coordination sphere. It will give the coordination number of your central metal atom, which indicate the negative ligands. So it always satisfies with the neutral or negatively charged. 5 points. You can write remaining things. You can write, right? Now, how the structures it comes, we'll see. CO, NH3, 6 times and Cl3. You tell me how many primary valency, which is the primary valency, which is the secondary valency. Which is the primary valency, which is the secondary valency in this complex. In this complex, which is the primary valency, which is the secondary valency. You tell me which is ionizable. Hello, if you are talking, it become very easy. Then we can go nicely. If
Sir,
you're not
plus
talking,
3 is the like the primary valency.
this will be primary valency. Which is the secondary valency?
Sir, inside the coordination sphere, the NH3.
This will be the secondary valency. So the primary valency, your Cl minus. So it will be ionizable. They are non-directional. It indicates the coordination, oxidation state of the metal atom. You tell me what is the oxidation state of this metal atom?
Sir, plus 3.
Hmm?
Plus 3.
How it's plus 3? Correct. You are right. Because x plus 6 into 0, it will become plus 3. So x equal to plus 3. Correct, ma? What you said is right. Okay. So this is the secondary valency. This is the primary valency. According to that chloride only, you can say it is a plus 3. That's why the primary valency will give the oxidation state of the metal. What is the coordination number? What is the
6.
coordination number? What is the coordination
6.
number? So 6 is the coordination number because 6 ammonia molecules are attached. But the 6 ammonia molecule, how it was attached, that will become a question mark.
Sir, monodentate.
It's a monodentate ligand. It become, the structure become like this. So they are direction. So it will have the octahedral shape. Shapes will be studied from BSc pair theory. Sorry, we will study in that valence bond theory. The 3 chloride, Cl, Cl, Cl. Okay, why I put it in the dotted line for the Cl? Why
Sir,
we are
ionic
putting-
bond.
Huh? They are non-directional. It may be present in this axis or that axis, that doesn't matter. Okay, that's why we are putting like this. Okay, so this is how you have to, they can give that structure of your coordination compounds. Now we'll go to the nomenclature of coordination compound and then we'll start the valence bond theory. Okay, nomenclature means according to IUPAC name, how the complex are naming. Okay. According to nomenclature, first one, order of naming events. Order of naming ions. So always cation mentioned first. Cation first, followed by anion. So first always, if you are taken K4 Fe CN6 this complex and Cu NH3 4 times SO4. These two complexes when you are taken here, which is the cation? First one, which is the cation? This become the cation. For the second one, this become the cation. So when you are naming here, you have to start with potassium. Here you have to start with the complex part. In the complex, the name cation, potassium is written first, followed by the name of anion, FeCN6 you have written. Likewise, in this complex, the complex was first written, and then you have to go for the minus. If it is non-ionic complex, the name of complex written in one word. For example, NiCO4, nickel tetracarbonyl. That's all. Nickel tetracarbonyl, cation anion. I mean ligands. Okay, ma? Is it okay? Is the first one. And the second, see, nobody answering. Is it okay?
Yes, sir.
Then naming of coordination sphere. Naming of coordination sphere. So in the coordination sphere, what you have? You have the metal atom and ligands, right? So it has the order. How to write name of ligand? Name of ligand first, followed by name of central metal atom, and then oxidation state. Oxidation number of metal in Roman letters. Oxidation number. So oxidation number of metal in Roman letters. So you come to here. So how to name this? Potassium. Okay. Next, next when you are coming this 6 cyanide is there. Hexacyano. First part cation first followed by anion. According to this will become the first one, potassium. And then coming to the coordination sphere, naming of ligand. How they to name the ligand? Hexacyano ion. What is the oxidation state? It becomes 2. Potassium hexacyanoferrate 2. That's all. Okay, for the simply. And the third, naming of ligands. Naming of ligands. So that's we discussed earlier. When it become negatively charged means, so negative means negative ligand means it has to end with the name which end with the O. If it's a positive ligand, it has to end with IUM. Okay, neutral, the name itself, name of the ligand. So except, so what is the exception? Ammonia and water. Ammonia you have to call it as amine, water you have to call it as aqua. Okay,
Sir, for positive ligand, what you have written, sir?
so your nitronium ion, NO2 plus. So here
Okay, sir.
nitrogen bearing positive charge, but oxygen will have the minus charge. So that oxygen will coordinate. Okay, so that nitronium ion you can set, and then NH2 NH3 plus hydrazinium ion. This NH2 going to be coordinate. This will not coordinate. Okay, and nitrosonium ion NO plus. Okay, so these are the positive ligands. Rare case more. It's become very very rare.
Okay, sir.
Okay, when you have the neutral ligand, for example, ethylene diamine means they will call it as En. Pyridine means Py. Water aqua, ammonia amine, NO nitrosyl, CO carbonate. Okay. Is it clear?
Yes, sir.
And then the fourth point, order of naming ligands. So first naming ions, naming coordination pair, naming ligands. Recording in progress. So next one, fourth one, order of ligand. Order of naming ligands. So first, how they name no before IUPAC, they will name first negative, second neutral, and positive. NNP, negative, neutral, positive. Because negative means excess. That's why they mentioned first. Neutral means the non-bonding electron involved. That's why second. The positive means one of the donor side only going to be there. So they will give like that. And now, according to IUPAC, so based on the alphabet, you have to name alphabet order. When all the ligands, இதெல்லாம் வந்துட்டு ஒரே டைப்ல ligands இருக்கு. Suppose you have ஒரு எக்ஸாம்பிள் எடுத்தோம்னா EN, CL, NO அந்த மாதிரி you have more than one ligand. So naming the ligand become question mark. So in a earlier case, they will give negative, neutral, positive. Now the recent advancement and then what we are following now is based on the alphabet order. So for the IUPAC convention, the name of ligand surrounding the central metal atoms are written in the alphabet order of preference, irrespective of the any negative, positive, or neutral. Okay, so you have ammonia, you have chloro, you have nitro means first amine, chloro, nitro. You have to follow that order. Okay, and then the fifth one has become numerical prefix. Numerical prefix to include the number of ligand. For example, here cyanide is the ligand, whereas it presents 6 numbers, right? Here cyanide is the ligand, it has 6 number. So we have to indicate the 6 number, no? So that's why we will say hexacyano. In case you have monodentate ligand, whatever number coming, you can indicate di, tri, tetra, penta, hexa, like that. Suppose if you have bidentate ligand, okay, example ethylene diamine, then here also you have one di. So ethylene diamine twice it's coming means now the naming has been changed into 2 mean bis, 3 mean tris, 4 mean tetrakis, 5 mean pentakis, 6 mean hexakis. So this is the naming of bidentate or polydentate ligands. Are you able to understand, ma? So I am writing. So if you have monodentate ligands, so the prefix should be di for 2, 3 for tri, 4 for tetra, 5 for penta, 6 for hexa. This is the order. Okay, for monodentate ligand. If it is polydentate, other bidentate ethylene diamond varudna. Now say CH2 NH2 CH2 NH2. This is the ligand. So we will call it, this become En. The En thrice. Now you are saying, how you say triethylene diamine? You should not say it's a triethylene diamine. Okay, you have to say bis. 2 means bis, 3 means tris, 4 means tetrakis, 5 means pentakis. So you have to tell tris ethylene diamine. So it indicates it's a bidentate ligand or multidentate, polydentate ligand. It is also one of the way we can find out. So bis means 2. Suppose En twice. So how to call it as bis ethylene diamine. So En twice means bis ethylene diamine. Okay? Okay? Is it okay?
Yes, sir.
And then the 6th point. Ending name. Ending name. So ending name, if the cation complex suppose if the complex is neutral or cationic complex, so no change in the name. For example, NiCO4, nickel tetracarbonate over, or CuNH3 4 times SO4. Here tetramine, copper 2 sulfate. So that's also no problem. Okay. In case it's a anionic complex, so the name should end with ATE. The name should end with the ATE. That sounds, it has to give that sounds. For example, K4 Fe CN6. It gives potassium. I'm not mentioning one mono, di, tri, because this is for oxidation purpose. That's why we don't need that. How much? Potassium Then coordination sphere. First cation and then anion. Anion is a coordination sphere. Now, if you are going to the coordination sphere, always first ligand and then next only you have to give the central matter. So how many ligands? Potassium, hexacyano. It's a negative ligand. Ferrate. Because it's a ferrous. Okay, iron 2 down on a ferrous. But because of the negative ligand, it becomes ferrate. We are writing it as a ferrate. Iron means ferrate. Cobalt means cobaltate. Nickel means nickelate. It has to end with like this. Okay? Okay, ma? And the last but not least, naming of bridging ligand. That means the ligand can donate 2 electrons. So the 2 electron can donate to 2 metals means that is called bridging ligand. Naming of bridging. So polynuclear complex means it may have more than one metal atom. Okay. So it may contain 2 or more metal atoms. So the ligand binding 2 metal atoms are termed as bridging ligand. So the ligands are common for the 2 ligands, 2 metal atoms are called bridging ligands. So such when you are naming that such ligand, the word mu can be added. Mu means bridging. Mu means bridging. So such ligand is separated from the rest of the complex by hyphen. So when you are writing complex like this, E and twice CO, CO not carbonyl, it's a cobalt. When it complex with NH, it also complex with number cobalt, and then OH, it complexes, and then E and twice. So this is the complex one. So we have to name this complex. How to name the complex? So both are 3 plus 3 plus only. So we have to come. How to common? No. Look here first. Here it was attached to 2 ligands. That's why bis, ethylene diamine, cobalt 3, mu imido, mu hydroxo, bis ethylene diamine, cobalt 3 ion. Okay. Okay. Or otherwise, you tell me NH3 4 times, cobalt, NH2, NO, cobalt, NH3 4 times, then whole thing that divided by NO3 4 times. Now you tell me how to say this. Tetra amine. One of you try this. Anyone try, ma? Tetra. So here I told bis ethylene diamine, cobalt 3, mu imido, mu hydroxo, bis ethylene diamine, cobalt 3 ions. So this is the name for this. Then you tell me what is this. So what is the number? It's a monodentate ligand, right? Nitish. Nitish,
Yes, sir.
you tell me what is the name of this ligand? Arshida. Arshida. What is the name of ligand, ma?
Tetramine.
Tetraamine. Very good. Cobalt 3. Okay. Then what is this? NH2. Here NH means imido. NH2 means
Amine, sir. AMN.
amido. Okay. So tetraamine copal 3 mu Sandhya. Tell me. Mu. Okay, anyone can tell Pop. Tetraamine
Mu
copal.
amido.
Mu amido and mu
Mu nitro.
nitro tetraamine cobalt 3 nitrate. When you have put this one into this, it will become 4 plus. So sorry, I have mentioned NO2. Okay, then it's nitro. NO2 here it's a monodentate ligand, no, both NH2 minus and NO2 minus, -1 -1. So it's a bridging ligand. It will contribute 1 1. That's why it's going to means it will give CO3 plus CO3. NH3 it don't give 0 0 contribution. Whereas these two will contribute. Okay. According to that, we will get the copal 3. So tetraamine copal 3, mu amido, mu nitro, tetraamine copal 3 nitrate. Okay. Okay, so next class I will send you that worksheet. You have to worksheet means we have to consolidate the names. Okay, next class we will discuss about the valence bond theory, and then crystal field theory and splitting of d orbitals, and then we'll go to the organometallic compound. Finally, we will discuss about the isomerism. So first, what is isomerism? What is isomerism? Tell me what is isomerism?
Branching.
Okay, so time is up. You can go and join the next class.